Hello, and welcome to this lecture where we're going to be introducing you to regression. So by the end of this session and the directed activities, you should have a good understanding of what regression is and when you would use it. So the different kinds of research questions it can help you answer, how it fits with different kinds of research design, and so on. You should have an idea of how regression works, what it can tell you and how you can probe findings further, and what to do if you find your data isn't behaving in a nice way, if it's kind of tricky data or messy data, which often real world data is. We'll also look a little bit at the minimum information that you need to report from regression and sorts of APA guidelines that you need to bear in mind for doing that. And finally, we'll look at the strengths and the limitations of regression. I'd say that regression is actually one of the most useful and most flexible kind of statistical techniques that you can have in your toolbox. So it's really worth getting to grips with it, and actually it would help you understand other types of analysis as well, things like ANOVA. They share a lot of similar approaches, and you'll see that a little bit from how it works when we get to that. So in the example I'll be drawing on today, I'll be drawing on my experience of doing quite a complex regression analysis in some respects for one of my PhD studies. So I conducted a quasi-experimental study. I looked at the way that different observer-related variables could predict the acceptance of myths, rape myths, and the perceived likelihood of experiencing rape myths that were gendered in particular. So I won't be going into too much detail about in that research. Obviously, it was on a sensitive topic, but I'll be drawing mainly on kind of my experiences of some of the issues I encountered, data assumption checking, interpreting kind of challenging output, and the decisions I made and how I made them. So I'm going to try and draw on that experience more than the actual findings of the research, if that makes sense. So what is regression? Well, it's not one thing, and it's also shouldn't be muddled up with that other kind of technique you may have heard of, someone regressing to a previous state or a previous life or something like that. We're talking about a set of procedures, a set of techniques that are used to predict or make predictions using some information that we have on predictions about how someone else will behave on another variable. So regression actually refers to a set of techniques. Now, there are different types of regression. We're going to be focusing on linear regression in this session, but there are other variables, there are other types of regression, and how you know which type of regression to use is really based on how your dependent variable is measured in the analysis. So we're going to be looking at linear regression, which assumes that you have a continuous variable as an outcome variable, as a dependent variable. So that means it must be measured at either interval or ratio level. So some people also refer to it as scale level data. If your dependent variable is actually something like a count, like the number of days of absence taken, particularly when you may have a large proportion of people that don't take any days of absence or sick leave, then you would need to do a different type of regression. And the ones that are sort of really good at handling that type of data, count data, so not using means but counts. The two that are really good at handling that sort of data are negative binomial regression and Poisson regression. However, if your outcome variable is a category, so perhaps you're doing some sort of analysis where you're trying to predict whether someone ceases smoking or doesn't, for example, following an intervention, you've got a categorical variable, they're in one category, they end up in one category or the other, you would do some form of logistic regression. So that there are different types of logistic regression. The example I've just given there is a binary logistic regression because your outcome variable is a binary variable, also referred to as dichotomous. So a categorical variable with only two categories. But if you had more than two categories, there are lots of other types of logistic regression, that you could use, including ordinal and multinomial. And if you look at something like layered statistics, I think they have some information about these that are on there, like forward-facing free pages. But they do also have a lot more detailed walkthroughs on their website, but you have to pay, I think, £5 for a month to access it. So there are lots of different types of regression, and it really depends on how your dependent variable is measured as to which one you're going to be using. The one that we are going to focus on is linear regression. Okay. So, what is linear regression? So, just like factor analysis and ANOVA, and actually MANOVA is a special case it's all based on the general linear model. So, linear regression is based on the general linear model. So, what that essentially means is it's an approach to describing data in patterns in data using straight lines. And so then if you know something based on these lines, you can make predictions if they're a good fit of the data. So linear regression, assumes that you have a linear relationship between the variables. And then what it does is it uses ideas of variance. So the way that as one variable, scores on one variable change, do we expect to see something similar happening on another variable, or so on? So it uses the idea of variance and correlation in order to kind of build on that. So regression is more sophisticated than correlation. If you're unsure about what those are, so variance I always think of as the spread outness of data. So what we're really going to be doing with the regression is trying to predict the spread outness of data in our outcome variable by knowing something else about some independent variables. But if you're not 100% happy with what variance is, I'd really recommend watching this video. It was co-produced by or co-created by Andy Field, and it uses interpretive dance to explain the concept of variance. And then building on that, they also have a video about correlation. So again, if you need to refresh your memory about correlation and what that is, so that's where two variables co-vary in a systematic way, then have a look at these two videos. So pause this video now and watch those two. They're only a few minutes long, and I think you'll have a much stronger understanding of what correlation is, and we can use that then to build on to explain regression. So I'm going to assume you watch those videos, so you're feeling more comfortable now about what variance and what correlation are. As I said, linear regression is kind of building on correlation, so it's more sophisticated. At its heart, it is all about correlations and variance, but it's more sophisticated than a straightforward Pearson's correlation, for example. What it's really aiming to do is to help us assess the predictive power of variables. So, if we know something about one variable, will it tell us something useful about another variable? Can we use it to make predictions? And so on. The way that linear regression works is that it can look at one dependent variable at a time. And we already know that that dependent variable, because it's linear regression, has to be continuous. You can have different types of linear regression. So if you only have the one independent variable, then that would be called a simple linear regression. So a simple linear regression is where you have one independent variable and one dependent variable. As soon as you have two independent variables or more, then we call it a multiple linear regression. And you'll probably see me calling it an MLR, or hear me calling it an MLR. So we've got these kinds of different terms, and actually some of the terms in regression are slightly different to other types of analysis that you may have encountered. So it's really important to get to grips with that, especially if you're reading through the literature or you're reading through guides, and if you're listening to me as well, you'll hear me using slightly different language to dependent variables. You'll hear me talking about predictor variables and outcome variables instead. And the reason for that is quite often in linear regression, all we're saying is that if knowing something about one variable, if we know something about one variable, it helps us to predict a change, a consistent change in another variable. What we're not necessarily doing is saying that that predictor causes the difference, the change in the outcome variable. So for a lot of the time, actually, if you look at some types of regression analysis, you could potentially swap what is initially labeled as a predictor and an outcome variable. You could initially swap them round, and sometimes it would still make sense. So it's a little bit like correlation in that respect. So a lot of the time we will talk about predictor variables and outcome variables rather than independent and dependent variables to move away from that kind of causal language in that respect. You'll see a little bit more about that later on. That's not to say that you can't try and make causal inferences with linear regression, but it doesn't absolutely nail it down. You'd have to have a really strong research design and a good theory to be able to make any kinds of causal inferences using regression in a confident way. As I said, multiple linear regression is usually abbreviated to MLR, and I'll probably be talking about MLR because it's slightly easier. The final thing, as I mentioned, variance. So I always think of variance as the spread outness of the data, as I've said, but technically what it is an estimate of the average variability of a data set. And what regression is going to do is help us to try and portion up these different aspects of variance into different, I suppose you could say causes, so what we think is going on, and that's how we can make the predictions. But you'll see more of that as we go on through the lecture. So MLR can be thought of in itself as an umbrella term. So we've already seen that regression can refer to lots of different types of regression. Well, even within linear regression, a multiple linear regression is actually an umbrella term. There are lots of different approaches within that. The ones that are most common are the standard linear regression, the stepwise linear regression, and a hierarchical linear regression. These are used in different circumstances. So the standard linear regression is often used in exploratory research where you believe there will be a relationship between the predictor or predictors and outcome, but you're not 100% sure what they're going to look like. And so what you do is you enter all of your predictors into the model in one go. You don't choose an order of importance to those predictors. You just put them all in and you have a look at the unique relationships between them and how they work together to help you predict your outcome. So it's very much used in exploratory research. Stepwise linear regression is also used in exploratory research, but rather than entering all of your variables in one go, the analysis, SPSS, actually uses a formula to look at different combinations of your variables to try and identify the most efficient set of predictors that help you understand your changes in your outcome variable. So stepwise linear regression, there are different methods of that. There's the backwards, the forwards, and the stepwise. So you've got a stepwise regression. I assume they ran out of names at that point. But the thing with stepwise linear regression is that it can be particularly useful if you're doing exploratory research and you've got a very large number of initial variables and you want to try and condense it down to make it more manageable. Well, stepwise linear regression can help you do that because basically the regression analysis will chuck out any variables that it thinks aren't pulling their weight in the model. So it makes the decisions for you. As a result, that makes stepwise linear regression quite controversial. So stepwise linear regression essentially does the thinking for you. You don't decide for yourself what you think are the important relationships. You let the formula do the talking, if that makes sense. One of the issues as well with stepwise linear regression is that it's more power hungry. So you have to have a lot more data to be able to do it than you would, say, a standard linear regression. So the take-home message is that really, unless you've got that scenario where you've got a lot of initial predictors and you want to whittle it down, then probably avoid using the stepwise linear regression because it's controversial. Now that leaves us with the final type of regression here, which is a hierarchical linear regression. And this is used often in a slightly different approach. So this is typically used when you either know the importance, the order of importance of the variables, and you want to enter them in that specific order so that the regression analysis will take account of the first variable, the most important variable first, and so on. Or sometimes it's used when you want to control for some potentially confounding variables that you can't control with, for example, by research design. So you've measured them and you want to take out their influence to start with, get rid of it, and then look at the things that you're really interested in. So if you want to control for some initial variables that you think are going to affect your outcome, but you're not actually interested in them, then people can use, or you can use, hierarchical linear regression. And the difference with this is that you enter your predictors in the order that you want to enter them in, based on your theory, and you enter them into different blocks. So if you want the regression to take into account your confounding variables first and get them out of the way, you'd enter them in the first block of predictors. You'd then start a second block and you'd enter the variables that you're really interested in, and you'd enter those into the second block. So there's a lot more control over hierarchical linear regression, but you tend to use it when you've got very specific hypotheses you're trying to test, or a specific model you're trying to test, or you're trying to control for something in a really specific way. So there are different kinds of multiple linear regression. But at this point, as I said, you may be thinking, well, that all sounds like a lot of hard work. Why can't I just do a series of correlations? Hopefully by now you're starting to get a sense of the way that regression can help you to test a range of hypotheses, potentially in one go, in quite nuanced hypotheses as well, so for controlling for some things and looking at others. So regression has a number of advantages over just doing lots of correlations. It's a more advanced technique, which means that you can unpick the relationships between your variables more, to a greater extent. So actually, it's more advanced in the, if we're taking a really strategic approach, it allows you to demonstrate more skill than just doing a correlation, but it can tell you more, which will often be of more interest to you in your research. One of the benefits of doing a regression as well is that you can predict a value on an outcome variable based on information on a hypothetical scenario in which you think someone will score this on variable 1, on predictor 1, they'll score that on predictor 2. What would I expect to see on their outcome variable? You can actually use regression to predict that, even if that hypothetical case doesn't exist in your data set. So it's quite a powerful tool if used properly. You can also use it to examine the unique relationship. So what multiple linear regression will do is it will look at how, if you've got 2 or more predictors, how they come together to help make predictions. But then it will allow you to also separate them out. And while controlling for the influence of the one predictor, it will allow you to look at the unique relationship between the other predictor and the outcome. So that's even true of standard multiple linear regression. Hierarchical does it in a more structured way, a more theory-driven way. But even in a standard linear regression, it will allow you to look at this unique relationship between a predictor and an outcome if you have multiple predictors in the model. So it can be really, really useful. You can also use it to test interactions. There are ways of creating interaction terms between categorical predictors. So you can have predictors in a, we'll come on to this in a little bit, you can have predictor variables that are either continuous in a linear regression or that are dichotomous, so they have 2 categories. You can't have a variable with more than 2 categories just entered into the model. You have to do something to it to make it work. But you can create interactions between 2 dichotomous variables, between a dichotomous and a continuous variable, and between 2 continuous variables as well. So it's quite useful in that respect. Obviously, it depends on your hypotheses as to whether you would do that or not. And one of the other arguments is that there's an idea that it can control family-wise error rate. So this is where each time we do an analysis in psychology, we say that if the p-value, that we identify as 0.05 or smaller, then we will say that that is a statistically significant effect. What that actually means is that if we did the same experiment 100 times, then 5 times out of that 100, we would make a mistake. We'd say that there was something going on when actually there wasn't. So that is a false positive. The issue is that every time that you calculate a significance test, that error rate is cumulative, it adds together. And so what can happen is, just by the sheer number of analyses you're doing, you can inflate the risk or you can inflate the chance of finding a statistical significance, even if it's just spurious. So there are different ways of handling that. And if you look at the Manover lecture, I talk a little bit about things like Bonferroni corrections. But we don't tend to do that in regression. And that's because the argument is that if we look at the model overall and we find that it is statistically significant overall, then that acts as a cap to saying, okay, then it's likely that there is something going on, at least at the individual predictor level. So we can look at that. If you find that your overall model, when you're looking at all your variables together, is not statistically significant, then it would suggest you shouldn't really go too much further. You might you should report what your predictor coefficients are, and we'll talk about that in a little bit. But you wouldn't interpret them in any great depth, because it could be anything that you find at that point could be spurious. Now, there are some critiques about that approach, but it is an argument that's made about regression. So if we think about kind of different approaches, we're starting to get a sense of how regression can fit different approaches, but these are actually some examples of sorts of aims or topics that are in the literature that regression has been used to help explore. So I've kind of paraphrased these, but there are examples out there. One approach was looking at the empathic functioning. Can we predict empathic functioning from personality traits whilst we control for positive and negative affect? So that was using things like a hierarchical linear regression, where you control for positive and negative affect first, and then you look to see if personality can predict uniquely something about empathic functioning. Also, people have explored using regression extrinsic career success, so things like title and money and those sorts of things, status, from personality and intelligence. And actually, some people have actually looked at that over time to see if these two things kind of change over different periods in people's life. And you can do that potentially with regression, because you can have standardized effects that you can compare between different models. There are issues with that if it's different people taking part each time, but it is something that potentially is possible. There's also research that's looked at things like sexual risk-taking in adolescence and looking at how self-regulation and attraction to risk can predict that. And then finally, what observer characteristics predict acceptance of gendered rape myths? Well, that was something that I was particularly interested in my PhD research. So when would you use regression? So thinking about the research design considerations, there are some really important things you have to think about when you are planning research and you're thinking of using regression as your analysis tool. One of the things is about independence. So what that is it's actually the independence of error in your model. But what it boils down to is that my score on the analysis, my score on the task shouldn't influence your score on the task. So if you imagine that we were eating a cake, the idea was that I was going to play different kinds of music in the background, and I'd see how much cake you ate as a result. What if I put a fresh cake out each time and kept everything else the same in the scenario? Then that would be one thing. But if I kept the same cake, and each time someone just took a chunk out of that cake, but because the cake got smaller and smaller, the people later in the study could only take smaller and smaller pieces, then it's likely that the way of predicting those scores, the person that came, I don't know, 12th in the task would have been influenced by everyone else who'd come before them, because there would be just less cake to eat, if that makes sense. So that's a nonsense example, but that's kind of what's going on with independence. Another good example is things like time. So if you've got something like a time lag, which is where you're predicting something across a period of time, you'd use things that, rather than linear regression, typically to do that, like time series analysis, that sort of thing. But things like predicting stock exchange results, well, they're influenced by yesterday's stock exchange results, that sort of thing. One of the other issues is about this idea of the control of spuriousness. You need to have a really good theoretical argument as to why you're including the variables that you do include in your model. If you look hard enough for random variables, you'll find patterns, even if they make no sense, and actually they're probably a result of something else going on. And that's this idea of spuriousness. So the way that we can control for that is by having really well-defined variables, so they're good operationalizations of the variables in our hypothesis. We've measured them reliably and accurately. We've included all of those variables that will impact on our outcome that are important to consider, but none that we've just chucked in for just to see what happens. So the research design considerations are basically the same as every research design, in that it's well crafted. The data considerations there, as I've mentioned, so your outcome variable has to be scale level, so or continuous, so it measures at the interval or ratio level. Your predictors have to be either scale level, or they can be dichotomous. So that means a categorical variable, but with only two categories. And we would usually code that as 0 and 1. Typically 0, the absence of something, or 1, the presence of something, or 1, the thing is labeled the thing that we're really interested in. But we'll come to that, some examples later on. But often it's easier to label things as 0 and 1 if you've got the two categories than 1 and 2 or anything else. But those are just some examples. We'll come back to that in a little bit. In terms of data behavior, now your data needs to behave in a particular way for regression to work. There are certain assumptions. It is a parametric test. There are certain assumptions that it makes about the data, and these are things like your error in the model, and this is really important. The error in the model, not the raw data, will be normally distributed. The error will be spread out at the lower end of your outcome variable as it is at the higher end of the outcome variable. So that would mean that the model is as good at predicting low scores on the outcomes as it is at high scores, and everything in between. So there are certain things your data needs to do, and some of that you can't know until you've collected the data. The amount of data is also important. We've already seen that the different types of multiple linear regression might require different amounts of data to work properly. That's another important consideration you have to really think about. And there's something else. If you're doing a multiple linear regression, you have to consider something called centering your variables. Now, centering is a really important concept. If you're thinking about entering any interaction terms into a regression, you need to center your continuous variables first. Centering variables can help with all sorts of different issues, including potentially independence issues. It can potentially help with homoscedasticity issues, and we'll come to all of these in a little bit. It can also help with multicollinearity. So if you've looked at the Manover lecture already, you should be familiar with what multicollinearity is, and actually also the factor analysis. So that's when you've got two variables that are so highly related to each other, it's essentially the same thing measured twice. And in this case, what we don't want is multicollinearity between our predictors. That's where the issue lies. So in MANOVA, we don't want multicollinearity across our dependent variables. In linear regression, we don't want it across our predictors. So centering can be a really, really invaluable tool. And the other way in which it's useful is that particularly you only need to really use this if you're doing a multiple linear regression. So I said earlier that multiple linear regression works. One of its benefits is that if you have a set of predictors, it will allow you to look at the unique relationship between one predictor at a time and the outcome, and it controls for the influence of the other variables, the other predictors. What it actually does is it holds all of those other predictors at 0. So it imagines that, okay, this hypothetical person scores 10 on this predictor, but everything else they score 0 on. What pattern would we expect to see? How would we expect them to be scoring on their outcome variable? Now, sometimes a score of 0 on a variable makes sense. So, for example, if you've got someone, one of your variables is about amount of daily exercise in hours, it's quite possible that someone does 0 hours of exercise. But if you asked someone on the PANAS score and you tried to hold their measure on negative effect at 0, that wouldn't make sense. 0 is actually something that isn't technically possible on the PANAS score on the scale. It's measured on a set of 10 items measured from 1 to 7. So the smallest amount you could score is 10. So it doesn't really make sense to talk about that negative effect at 0 because it's not really something necessarily that's possible. So this is where, again, centering comes into play. And there are different approaches to centering, but the one that we're often going to use is something called mean centering. And this is where you change your initial raw data into deviations from the middle, the average score. So you take each person's actual score on the variable and you take away the group's mean score from it. And then what it means is that some people will be, dead on the mean score, some people will be higher, some people will be lower. And then it turns that mean score into the 0. So when regression is technically trying to hold all of your other predictors at 0, that's actually the average score on the other variables. I know it sounds a little bit complicated, but if you have a look at Andy Field's book and you look at his section on centering, I think it will help make a lot more sense. I've also got some resources in here where they talk about centering and when you would use it and why you would use it. Some blog posts which are quite friendly and easy to use. But centering is something you should also consider. It's not necessarily a data assumption check itself, but it can resolve a lot of issues in terms of violations of data assumptions in regression, and also making multiple linear regression a lot more easy to interpret and more meaningful. So, as you're thinking about this, then you need to consider which kinds of approach you might be taking. So standard, stepwise, hierarchical, and this will be based on kind of what you particularly want to find out from the data. So the kinds of research questions that you're trying to answer. As I said, the approach that you take with this does have an implication for sample size. And one of the things with any type of analysis is that if you do not collect enough data, you run the risk of simply not finding anything statistically significant purely because you don't have enough data to see it. It would be like trying to find something. If you've got a really huge relationship between the variables, you'll be more likely to identify it. So that would be, say, if we had a huge relationship and we could look at, a street sign down the end of the road, we could just look at it potentially with the naked eye. But if we wanted to be able to explore something a lot more, a lot smaller than that, maybe, dust mites, we'd have to have a magnifying glass. We'd have to have a microscope that would massively increase the magnification then of what we're trying to observe. And that's essentially what we're trying to do with sample size. The more data you have, the smaller sized effects you can detect if they're really there. With regression, we're quite fortunate in that there are lots of ways of doing this. So there's a really useful tutorial by UCLA on their G-Power kind of pages for calculating multiple regression, so how much data you need. You can do this yourself using G-Power, and the recommendations are that it depends if you're really interested in looking at the predictors as they come together as a model, then you would estimate the sample size based on that. But if actually you really want to detect the unique relationship between one predictor whilst you hold constant other predictors, that will require more data, so you base your estimates on that instead. And you can use G-Power to do that. But actually, Andy Field has got a set of 3 really useful graphs for detecting small, medium and large sized effects based on models with different numbers of predictors, and it gives you a really good guide as to how many participants you'd need in each of those scenarios. So I would recommend using Andy Field's book, certainly in the first instance, just to get an idea, but you could reference that if that's kind of the guide you've used to help you identify sample size for a proposal, that sort of thing. So, okay, what did I do? Well, I actually performed a hierarchical multiple linear regression. What I wanted to do was to control for some of the attitudinal variables. In this example, things I believed that would have an effect, things like gender-linked social roles, and then demographic variables. For example, some research suggests things like highest educational qualification attained is a good predictor. So I wanted to control for those, and then I wanted to look at the impact of observer gender on gendered rate myth acceptance. But I also wanted to include a pre-manipulation check. So my study was quasi-experimental, and I wanted to see if basically the groups in my analysis were similar before the intervention, and therefore if there is any change in the any differences on the way that people accept different types of rate myths, then I could be more certain that it was because of the intervention, the kind of the randomization, the different conditions I put them in afterwards, and so that's what I was really interested in, using this hierarchical multiple linear regression. So actually I had a set of hypotheses that I wanted to test. So 1A to 1H, which was part of a first research question, and I conducted a series of hierarchical multiple linear regressions where I entered them into 2 steps. As I said, the attitudinal and demographic variables first, apart from observer gender, and then the observer gender and the pre-manipulation check. And then later on, I used the predictors from that, which I'd identified as really strong predictors of these attitudes towards gendered rate myths. Then I used that to help me select out a smaller number of variables, which I followed up to test the experimental effects in the rest of the analysis, which I used with ANOVA. So you'll see here actually I was using a combination of different statistical techniques to test different things. And that's quite common, especially if you've got a range of hypotheses you need to test. You can't always find a single test to do all of that. So what you need to do is have a good plan of for each hypothesis, how exactly you're going to test it. And it may be that you have to do a couple of different types of analysis in order to achieve that. And that's what I had to do in my study. So how does it work? It's really, regression is quite an iterative process. Okay, so it's a little bit like factor analysis in that respect. But what it involves is building a model, fitting that model to the data, and seeing how well it fits. Is it a good description of what the patterns you see in your data or not? And then identifying which of the predictors are telling you the most in that model. And then once we've kind of refined our model, we've gone through and looked at it, it may be that we can make additional predictions about how hypothetical cases would score on an outcome based on information from a set of predictors. So what does it mean? Well, as I said before, linear regression is all about putting straight lines on things. So if we imagine that we're presented with the graph to the left of the page, we have a symptom index from 0 to 160. We've got some mystery drug called drug A, and the x-axis there along the bottom is the dose in milligrams. So the symptom index is along the y-axis of the graph. What we've got here is a data point for each person. So we've seen what they scored, what dosage of drug A they took, and then their respective symptom index score. And what we can see is that there is a downward trend. So from the top left, going to the bottom right of the graph. So that suggests that there's a negative overall trend between the two variables. But if I just presented that graph to you, it would be a bit like, well, okay, so there's a lot of data points. They kind of all look a bit wiggly, but sort of going in the same direction. What we can actually do to help us describe that better is to start using a straight line. And so you can see in the right hand side, we've got the same graph, but this time we put a line of best fit on it. So a straight line that most accurately fits as many of the data points as it can whilst remaining a straight line. We can see actually that each of those data points sits very close to it, not necessarily perfectly on the straight line, but very close to it. And so this is where regression starts to come into its own. So all we're going to be doing really is using the line of best fit. We're using the equation for the line of best fit, and this is really where simple linear regression, this is a simple linear regression, and we can build on that when we have more than one predictor and so on. This is the heart of it, how regression works. So we have a formula here where we're trying to predict y. So y is our outcome variable score. And then we've got a series of other expressions there. We've got, or terms, we've got b times x, multiple x by x, plus a. So in this example, b is the slope of the line of best fit. X is whatever we scored on our independent variable, and a is the intercept. So if I draw these on, so the top arrow is the intercept of y, and that is where the line of best fit would intersect the y-axis on our graph if we drew it all the way across. And then what we've got, b, is the slope of the line of best fit. So is it very sloping? Is it quite gradual? That will give us an idea of the relationship between the variables. And we can actually then plot out all of these values, and we could use it to predict y. So what we would have is b, the slope of the line of best fit, and we would multiply that by whatever our hypothetical case would score on x, so maybe 100. And then we would use the straight line to see where a would intersect on the graph, and we'd say, okay, well, if they've got a score on x of 100, then they're probably going to have a score somewhere around 120 on the index, symptom index, or something like that. But what regression does in SPSS, luckily, is it estimates things like A and it estimates things like B for you, and then you could create this. Now, the one thing that is excluded from here is E. So E is the error term, and it doesn't matter what type of analysis we're doing or how we've measured our variables, how accurately. It doesn't matter even how good really this line is at fitting all the data points. You see that this data point is quite a lot further away from the straight line than the others. Well, that would represent an error in the prediction. And so in a proper regression equation, there would always be a term for error. Okay. But the principle stays the same. And actually, again, what we know is that if we run the regression in SPSS, it will produce the estimate of error for us as well. And we can use this formula then to predict a hypothetical case, their outcome score. Okay, so we're starting to get a sense. Okay, so if we like it, then we need to fit a line to it. Sorry, I'm thinking of the Beyonce hit. If we've got a graph, we need to describe it. Okay, so we put a line of best fit on it. Okay, what does that really mean? Well, as I said, in this first example, which is the same as we've seen on the other slides, what we can see is that each data point fits very closely to the line. They're almost all on it, or they're very close to it. We would look at that and think, okay, that's a really good description of the data, that straight line. If we look at the example on the right-hand side, we can still see that the line and the general kind of trend of the data points, they seem to be saying something similar, but actually each of those data points is further away from the line. So what we know from here is that the one on the left, the straight line, represents a very good fit of the data. The one on the right represents a moderate fit of the data. Okay, so now we're starting to get a sense of how the error comes into this, why error is important. So whenever we fit a line to something, there's going to be a difference between what we predicted the person would score and what they were actually observed to score, for example. So we might predict that someone with a score of 50 would score on the intent syntax 140, but actually they scored down here, which is 135 or something. So you can see there's a bit of a difference between what our model would be predicting you would score and what our model has actually observed that you score. So what is actually observed in the data. And so what you would do in a regression is you measure this difference. You measure the distance of the line of each data point, the predicted value, the line, and you measure the data point, how far away it is from that. And these red lines represent the error in your model. And so these are the distances in the model, in the prediction. So what we need to do, though, is quite often now we've got some values that are going to be a positive and some that are going to be a negative. Well, in terms of regression, if you cast your mind back to the correlation, if you were looking at anything by, say, Eugene O'Loughlin, and he takes you through by hand how to calculate things like regression and correlation. If you look at his videos, you'll see what I'm talking about. But that isn't very helpful, because if we just added some of these together, you'd have some positives, some negatives. They're going to cancel each other out. And they wouldn't really give you a good idea of how far away each of these data points from the line were, because they just cancel each other out. So what we have to do is take this measurement and then square it. As soon as we square that value, it takes the direction of the difference out of the picture. And actually what we would then do is you sum the squares for a particular effect and so on. And so when you see people talking about sums of squares in ANOVA, in regression, in MANOVA, this is essentially what it's doing. In ANOVA, they're taking the difference between the group mean and a data point, or the grand mean and the data point, and so on, or rather the grand mean and the group means. But the principle's the same. So actually what we always end up with in things like regression, we're trying to end up with different sums of squares, and we try and attach that to different effects. Okay. So that's a bit of a long-winded explanation, but it gives us an idea of what we're trying to do with this line, what the value of this line is. We're trying to get an idea of how well this line fits the data, so we know how well it would predict scores on an outcome. How far away from, can we expect our prediction to be from the real score on Y based on what we've already observed. And so this difference between predicted and observed value is called the error, but it's also called the residuals. Okay, it's the bit left over. And that is really key. The residuals are how we check an enormous amount of the data assumption requirements then of regression, but also things like ANOVA, particularly with complicated designs in ANOVA and MANOVA and so on. So what regression does is it takes these initial sums of squares, it turns them into mean squares, and it starts to portion up variance according to different effects. And so before I go any further, I think it would be really helpful to have a look at these videos by Eugene O'Loughlin. So in these, he talks about calculating correlation by hand, and you'll start to see how these sums of squares come into play, or how squared values are used in correlation, which is the backbone of regression. And then Eugene O'Loughlin also does have a calculating simple linear regression by hand, which is on his website as well. So I maybe watch that one afterwards, but you're welcome obviously to watch that now. If that's how you prefer to learn by doing by hand, then please do feel free to pause this video now and have a look at those. So what we'd also, you don't need to know this, but if you wanted to calculate the slope of B, the slope of the regression line for each of your predictors, or if it's a simple linear regression for your only predictor, then it would be B would equal R, which is the Pearson's correlation coefficient, divided by, or R multiplied by the standard deviation of Y divided by the standard deviation of X. So Y is your outcome variable, X is your predictor. So that's how you calculate the slope. You could calculate the intercept, so the point at which your line of best fit intersects with the y-axis, by saying that A equals y, mean y minus B times mean X. So you honestly don't need to know that it's just if this helps you to understand what's going on. For some people, and particularly initially, when I was learning about regression, that just looked like gobbledygook to me. So it's there if that's how you learn, but ultimately regression, SPSS will calculate these things for you, and it's a lot more about how you use that information than necessarily being able to do it by hand. But for some people, I know they prefer to learn it that way. Okay, so we've got a graph. We can imagine the line and how far away the data points are from it. But that's still very hard to try and explain that to another person without telling them exactly the difference between the predicted and observed values for every single one. Or if I started spouting the sum of squares at someone for a model, it wouldn't mean anything. So what we actually need is something else that we can use to describe what that line of best fit tells us and how well it fits the data. So we get a sense of how good our predictions would be. And that value is the R squared value, which is represented by a capital R squared in italics. And what this value represents is the amount of variance in our outcome variable that is accounted by the line of best fit. So it always takes a value between 0 and 1, or not, it doesn't always, but it usually does. There's something wrong going on in your data if you've got a minus figure. It can happen, but it's not a good sign. But usually it will be between 0 and 1. If you multiply that by that value that you observe the SPSS produces for you by 100, it actually gives you the percentage of variance in your outcome variable. So the range, the variability, the spread outness of scores in your outcome variable that can be accounted for or explained by your predictor or predictors. So if we imagine then, if you had an adjusted R squared of 1, it would mean that you've got a 100% accurate line of best fit. It means that every single data point lines perfectly or aligns perfectly with that line. It is a perfect predictive relationship between X and Y. If you find that with your data, something's gone wrong, particularly in the social sciences. There is something fishy going on. It may be that you've got, if you've got you might have a perfect relationship that's negative or positive, but it implies that the line of best fit would provide an excellent description of your data and an incredibly accurate prediction of an outcome score based on knowing something about the predictor. As I said, this is not usual. But what the R squared value can do is it gives us an idea of what's a good fit and then what's a moderate fit. Okay, so we'd expect to see a much higher R squared value on the left-hand side graph than we would on the right-hand side, but actually the right-hand side is still pretty good. Now I want to give you an idea of what that looks like. And I found a really interesting website that has an interactive regression plot. So I'm just going to open this up. Okay, so this is the interactive regression plot. So what we start off with, we've got n, which is our sample size. Well, we've got 0 on there for the moment. We don't want to fit our own line. We want it to automatically start fitting a line for us. We do want it to display a line of best fit. So we start off with R, which is an idea of the correlation between the variables, and then Y and so on. So if I just start drawing a couple of points. So imagine this is our line. I'm deliberately trying to choose plots that fit very close to that line. So what we can see here is we've got a line of best fit, which we've got what each variable, so case 1 where it scores and so on. We can see that we've got a negative relationship between the variables and so on. What we'll show the residuals, so it gives us an idea of how different. So you can see that some of these are positive, some of them are negative, and so on. But we get an idea of the residuals and how across different aspects of our x variable and a y variable, it started to plot the residuals for us as well, and that's actually how we can start to check data assumptions. But I won't go into that right now. So if I close that. So it just gives you an idea. Whereas if I start to draw these kind of lines out here, you get an idea of, well, at the moment it's the R value, but we could square that to get the R squared. But what we can see is, that has gone down considerably. Okay, so it's a negative correlation, but it's gone down considerably from kind of 0.9, very, very, very strong, to 0.7. And so on. So you can see that the effect that these more spread out scores are having on this line of best fit. And actually what we've got here is, this is the equation for the line of best fit. So our prediction of y is equal to the slope of this line here, that's the estimate of that, multiplied by whatever we score our x, plus the intercept. So that's the point at which our line cuts across the y-axis. I'm going to come back to this in a little bit, so I'm going to reset that now, but I'll come back to that and we'll talk through that again. It's a really useful tool. Okay, so R squared, we're going to start to see that R squared is, essentially R squared is R squared. So that value, as I said, we can take the R value and square it to get our, and then multiply that by 100, and it gives us the amount of variance in our outcome score that is explained by our predictor or predictors. Now, one of the issues can be that R squared can be what is called an upwardly biased estimate. So it's fancy talk for saying it can be a bit generous. It can overestimate the amount of variance that's explained by your model in your outcome variable. If you're just trying to describe patterns you find in your sample, then that's nothing too concerning. But there is some guidance that suggests that actually the adjusted R squared that is produced by SPSS at the same time as R squared can be slightly more robust. It's usually slightly smaller than R squared, and as such, there's an argument that if you want to generalize beyond your sample to the population the sample is supposed to represent, then using the adjusted R squared value is probably better, it's more robust. If you saw a massive difference between your R squared and adjusted R squared when you produce your output, then that could be a sign that there's something funny going on with the data. But quite often they'll be very similar to each other. As I said, it's typically slightly smaller. Now you might be looking at this thinking, okay, well, what's the cutoff then? What percentage do I get that is like, oh, that's a good model? So is it like over 70% that's a good model, or what? And unfortunately, there isn't a hard rule for this. You have to understand the context of your research. Now, it may be that in some contexts, 10%, being able to consistently explain 10% of the variance in scores is meaningless. It may be that it just doesn't really help you do anything. But in other contexts, being able to explain 10% of the difference in scores could be really important, perhaps in some measure of suicide ideation or something like that. 10% could be really meaningful and have a practical impact. So the R-squared value can help you to identify whether your model is likely to be useful to you, but you have to always do that based on the context of the research, the data, the population, and your research question. There isn't a set criteria that says when you get over a certain percentage that's good and anything below that is bad. So it makes it slightly more complicated, but you just have to be aware of that. Well, okay, so we've started to get an idea of, well, it looks like our model might be, fitting the data well, but so what? How useful is that to me? So I can explain 40% of the variance in an outcome variable. Well, does it do that reliably? Is that what I just get by chance if I just use the mean score on the on my outcome variable just to guess what someone would get? Would it be better to use this regression model or just guess using the mean score of my outcome variable? Well, we need to test it essentially. So what we want to know is basically, is the model better? So is there something that is more useful in predicting an outcome when we know something about another variable or a set of variables than just guessing? And actually how we test for that in regression is we use an F ratio. We perform, SPSS performs a special case of ANOVA on our data. So if we think back what the ANOVA does, it produces an F value, and that F value is actually a ratio. In this example, when you're thinking about regression, it's actually looking at the ratio of the amount of variance that is predicted accurately by the model versus the amount of error in the model. So if it's better at predicting than it is at making mistakes, then your model will be statistically significant. If it makes a lot more mistakes than it does get anything right, it's not going to be statistically significant. So by and large, the larger your F ratio, the better the model is at predicting an outcome variable, and the more likely it is to be statistically significant. That is, it would outperform merely guessing someone's score on Y from knowing the group mean. So it gives us an idea now. We're starting to get a picture of what the regression's doing. It tells us how well our model fits the data, how accurate it probably is in predicting, and it tells us whether it would be more consistent than just guessing using a mean variable. So is there something genuinely going on between the variables or not? And how the F ratio is kind of written in this context is the mean squares of explained variance over essentially the mean squares over unexplained variance error in the model. And so that's where those mean squares come in. But I'm not going to labour the point with that anymore, but if you want to explore how these things work, I'd recommend looking at Batchik and Fiddle's chapter on regression. They go through these kind of really core equations that underpin regression, and they provide examples on how it's calculated. But they only do that for multiple linear regression. Okay, so all right, fair enough. You'd be thinking, okay, well, what does that look like in practice? Well, this is actually a table that was taken from one of my PhD chapters. So you can see in there that I've done a hierarchical multiple linear regression. I'm only going to look at the first part of this. So dynamics of rape was the subscale, the types of myth, and these are myths that are particularly linked to gender. If you're interested in reading about that sort of thing, please let me know, and I can point you in the direction of some literature, but I won't go into too much detail about it. But there are stereotypes about victims and survivors of sexual violence that are particularly related to gender and who can and cannot be a victim or a perpetrator. And so I've got in here A hierarchical linear regression I've called the first step, step 1, and it's where I put my control variables in. Things I wanted to put in, kind of get out of the way so I could look at the other bits that I was testing for that I was really interested in. So the first thing we can see is that I've got a column for B. Well, B is actually the slope of our line. SE of B is the standard error of B. The next column over is actually the symbol for beta, but we'll come on to what that means later. I've got a column for our p-values for each of the predictors. I've got the unique percentage of variance explained by each of those predictors, and I'll tell you how to calculate that. And I've also got a value for a VIF score, which I'll talk about that later. So you're starting to see, well, okay, so I've got my B values that have been calculated. But for the moment, I'm not interested in that. I'm looking at this overall model. So when I consider things like gender-linked and gender-transcendent social roles, socially desirable responding, sexual orientation uncertainty, I've got a variable of sexual orientation identity. Now I've done dummy coding here, or actually I did weighted effect coding. I'll talk about that later. But I had to handle that in a special way because I've got 3 categories. I couldn't just plop that into the regression, it wouldn't work. I've also got information on ethnic background and highest qualification and so on. So if I could take all of these things together, does it give me an idea of how much variance in these dynamics of rate myths that allows me to account for? So I've reported the adjusted R squared, and what I've got is a value there of 0.243. So if I multiply that by 100, then in all, that accounts for 24% of the variance in this score. We also know that I've got my F ratio here. So these 2 values are the degrees of freedom. They're based on the number of predictors in the model and the number of participants in the model. They're based on that. And that's used to calculate my F ratio, and that is used to calculate my statistical significance. So we can see that I've got a model that accounts for 24% of the variance in dynamics of rate myths. That is statistically significant, so it's likely to be consistent at doing that. So that was a good thing. When I got my analysis results, that was a positive thing to see. It did appear to me to be able to predict a meaningful amount of variance in understanding how people respond to gender and stereotypes and so on. So that gives you an idea of how you would use that information in practice. Okay, so what if we've conducted a multiple linear regression? We have looked at the model overall, as we've just done there, and we found that we have a statistically significant model overall, as this example does. What do we do next? Well, we need to start to look at our predictors. We need to look at the unique relationship between a predictor and the outcome variable, and we need to understand what that looks like. We should only really start unpicking the relationships between predictors and outcomes if that overall model is statistically significant. If it is not statistically significant, then the argument is that we could just be identifying spurious relationships if we then go on and do lots more significance testing for individual predictors. So that's where that idea of the cap for the family-wise error rate comes in. Now, one of the things I should say here is that each of these variables was actually centered. So I centered each of these continuous variables before I entered into the model, because it means that when I'm looking at the impact of gender-linked social roles, and I want to look at the unique relationship between that and that predictor and my outcome variable, it's holding all the other continuous variables constant at 0. But what that means now, because I centered them, is it's actually holding them at the average score in the data set for each of these things, because I've mean centered them. And so that makes it a lot easier to interpret the results. So I centered each of these continuous variables before I entered them. You don't have to do it for categorical variables, it doesn't make sense, but I'll come back to how you use multi-categorical predictors in a little bit. So what that allows you to do is it allows you to look at the relationship between a predictor and an outcome, the unique relationship, to see if it is statistically significant. So on its own, does it predict some variance, statistically significant amount of variance in our outcome variable or not? It allows us to understand the direction of the relationship between the variables. So do we have a positive relationship between predictor and outcome, or negative? So if it's a positive coefficient that we get, our b-value, then that suggests that as scores increase on the predictor, scores are also likely to increase on the outcome variable. Whereas if it's a negative coefficient b-value that we identify, then that suggests that as scores increase on our predictor variable, scores will decrease on our outcome variable. There's an inverse relationship between the two. Now, a benefit as well is that we can actually compare the size of the relationship between the predictors and outcome and decide which relationship is strongest. And that can be useful if you're thinking about using your findings to help with an intervention. It might suggest where the biggest payoff would be. So if you concentrate on one of the variables in comparison to the others, you may be more likely to see a bigger impact if you can change that on the outcome. It's not always the case, but it can be a way of helping you to make those sorts of decisions. So how do we do that? Now, I've already been talking about b-values. So we know that a b-value represents the slope of the line of best fit for that predictor. A b-value is measured in the original units. So the units that the predictor were originally measured in, and the outcome that the scale the outcome was originally measured in. So we call those the raw coefficients. Now, you also, when you run a regression in things like SPSS, you will also have standardized coefficients. And these are things where they are referred to, they represent, rather than things in the original units of measurement, they represent things in standard units, essentially in standard deviations. So we call the raw coefficients, the unstandardized coefficients, b-values. They are in the original units of measurement. And we call a standardized coefficient, standardized coefficients, the things that are measured in standard deviations or units, we refer to that as the beta values. And that's the symbol for beta there. So we're starting to get a sense of, okay, so we get an idea of we've got these b-values, these beta values. Associated with the b-value, you also have a test, a statistical significance test. It's actually a special case of a t-test. So what that does is it looks at the value for one of your predictors that's denoted there by the letter J, the slope of the line of the predictor J, divided by the standard error of B, the slope of the line of predictor J. So it's the the B value divided by its standard error. That will give us a t-value, and if that t-value is greater than 2 or minus 2, then it will be a statistically significant result. And so actually what the b-value also allows us to do is to test the significance of each predictor. What it's actually doing is saying that the slope of the line is significantly different from 0. So if the slope of the line was 0, there wouldn't be a slope. It would be a straight line. It wouldn't predict anything. So the further away from 0 the slope of B is, the more likely it is to be statistically significant, and so on. So that's how we get our test of statistical significance. Okay, so what does that all mean? So how do I really interpret a b-value or a beta value? What does it mean in practice? So I've already said that a b-value represents the original units of measurement. A beta value represents the standard deviations or standard units. So what a b-value tells us is for every 1 unit change in a predictor in the way that was originally measured, what change could I expect to see happen to the outcome variable as it was originally measured? So if we have a look at this example here, so we look at the first predictor in the model, which is gender-linked social roles, and we'll look at, we've got b-value there of minus 0.009. Okay, so what does that mean? So that's in the original units of measurement. So I would expect to see for every unit increase on the scale on gender-linked social roles, so every point they go up on that scale, I would expect to see their rejection of the dynamics of rape myths go down by by 0.009 of a score. So that was the subscale of that was a subscale of questionnaire that was measured using a mean score. So I'd expect to see their mean score go down by 0.009 of a point. So it doesn't actually sound like a lot, but you know, it's sadly the way things are in the world of the PhD. So it gives you an idea there. So if you can see that that coefficient is negative, the value in that coefficient in that column for that row, that cell of the table here is the change in the y variable, the outcome, which is the dynamics of rape, the rejection of rape myths. I would expect to see that change, and I know that it would be a decrease. So they would become less rejecting. So the more they endorse traditional gender-linked social roles, the less rejecting they are of dynamics of rape myths. Okay. So that gives you an idea. Okay, the thing in the brackets is the standard error of B. Okay, we don't need to worry about that too much, but that is what is used as well by SPSS and so on to calculate confidence intervals. So this was actually part of a massive table, so I didn't have room to put the confidence intervals in, but if you can, it's a good idea to insert them. Okay, so that was the B value in the original units of measurement. Let's have a look at the beta value. Okay, so what we can see here is our beta value. That's the standardized coefficient. So it's referred to, it represents a standard units for, so that means that for every standard deviation increase in gender-linked social roles, I would expect a person's score on the dynamics of rape myths, on rejection of dynamics of rape myths, to go down by 0.321 of a standard deviation. Okay, so you might be thinking, well, why on earth would I ever want to know that? There are a number of reasons why the standardized coefficients are useful. There used to be an argument that ideas about, practical value of applying, the B values were for practical application, and the beta values were for kind of theoretical relationships. So, developing one practical applications or theory. What we do now is provide them both because it allows the reader to use them in the way that they need to. So APA recommends that you report both of them. So another benefit of the beta value is, you'll see in a moment, that you can actually compare the size of coefficients. You can't do that with a B value because they're measured in different units to start with. So if something's bigger than another variable, it just might be because of the scale of measurement used. It's got nothing to do with the actual inherent relationship. So you cannot compare the size of relationships necessarily using the B value, but you can compare them directly using the beta value, which is again another reason to have them. So let's look at this example then. What I'd like you to do is have a go. So pause this video, try and interpret what you think the B value is telling you there for the gender transcendent social roles variable, about scores on rejection of the dynamics of rape myths. Have a go at what you think the beta value is telling you, and then have a go at telling me what you think, which of those two variables is the stronger predictor, is doing the most work. Okay, so pause this video and have a go at that now. Okay, so what we can see here, we have to remember, this represents the unit of change we'd expect to see on our outcome variable based on a single unit increase on here. So for every unit, every point we go up on the gender transcendence social roles subscale, we would expect to see scores go down by 0.011 of a unit on rejection of dynamics of rate myths. So we would expect to see again a negative relationship between these things. So hopefully that makes sense. If we're looking at the beta value, what we can say is that for every single standard deviation increase in gender transcendent social roles, attitudes, we would expect to see a decrease of 0.254 standard deviations on the rejection of dynamics of rate myths. So you're starting to get a sense of what's going on. Okay, so now we're going to look at what this means in terms of the relative size of the importance of these variables. What we can see, you can ignore the direction of the beta value. It doesn't matter if it's positive or negative. That doesn't tell you about the size of the relationship, just the direction of the relationship. You can see that this value here, 0.321, is larger than 0.254. Therefore, this is actually the stronger predictor in comparison to this one. So it gives you an idea of which is the stronger predictor of the two. This has got a stronger relationship in comparison to this one. So that's starting to give you an idea of what you can tell from the predictors in the regression. Now, I've already mentioned a few times that a predictor can either be continuous or it can be dichotomous. You can't have multi-categorical predictors, just use them as is in a linear regression. It won't work. It will think they are something else. It will think they are a scale level variable, and it will treat them accordingly, and it will churn out nonsense. So what we have to do is we have to change our initial one but multiple category variable into multiple two category variables. Now, there are different approaches to doing this. The simplest and the one that you've probably come across is called dummy coding, or sometimes it's called indicator coding. And this is where, as I've already mentioned, you code one category as 0 and the other as 1, and whatever is category 0 is your reference category, and you compare your whatever's coded 1 to it. And so dummy coding is the most commonly used. It's the most straightforward to set up. Now, there are other alternatives to that, including effect coding, contrast coding, and weighted effect coding. Now, I actually used weighted effect coding in my PhD research because I had very unequal group sizes in terms of male and female participants, and I needed to account for that when I did my analysis. I wanted to account for that because it's a problem with the literature. Quite often they are female bias samples, but people don't take into account that when they're calculating the results. So I used weighted effect coding, but there is another alternative, which is effect coding. And whereas dummy coding compares one category to the other, effect coding essentially compares them to the grand mean. So it will give you an idea of whether some categories is higher or lower than the average. So they tell you slightly different things. If in doubt, I would just stick with dummy coding, particularly for if you've only got two categories anyway, then just do dummy coding. But if you've got multiple categories and it doesn't make sense to try and compare them to a reference category, there isn't a reference category that's meaningful, then things like effect coding, if you've got equal numbers of across your categories, or weighted effect coding, if you've got very unbalanced categories, can be an alternative. I'm not going to go into that too much detail. It can be a bit challenging to get your head around it at first, particularly the effect coding, but it's important to understand it. What it means is that you'll initially start with one variable with multiple categories, and then, as I said, you'd end up with multiple variables with only two categories. So if you have an initial categorical variable with 4 categories, and you did, say, dummy coding, you'd end up with 3 new dummy coded variables. So 1 less variables than there are the number of categories, and so on. So actually, if you know to start with, you're going to want to include a multi-categorical predictor in your regression, then you've got to account for the number of additional predictors you're technically going to have to add into the model. That will affect your sample size calculations. So it is something you have to really think about carefully before you finish your, before actually you should go out and collect your data, but certainly before you finish it. There's a really useful couple of websites here. So Grettenhaus et al. 2017. If you look, they have a paper where they discuss this, and there's the website. They've actually got a whole range of Excel spreadsheets that show you to give you an illustration of how these things work. They've got some examples of syntax that you can use to recode variables and produce these sorts of things and so on. And I used that when I was doing my PhD. So the other one is UCLA's web pages, and they describe all the different kinds of coding that you might want to use, and they give examples of when you might want to use it. So if you're presented with this, you've got a multiple categorical variable, perhaps you've got you want to look at ethnic background, and you've got census categories, and it doesn't make sense necessarily to have a reference category, then it may be that you need to take a different kind of coding approach, and I'd have a look at those web pages to see what's out there and which ones might work. Okay, so imagine that we have got, now I've just pulled this out of an old example, but we've got, this is an example of a coefficients table that's produced by SPSS. It's quite the most basic version. And we imagine that we have got a categorical variable. There's only the two categories. We've used dummy coding. So we've got our categorical variable there is gender. We want to look at the unique relationship between gender and a measure of blood pressure, controlling for age and stress levels. Okay, so we know that we've used dummy coding, and in this case our reference category is male, and our female category we've labelled that as 1. So okay, what do we do? So for every unit we increase on gender, we go down by 1.6. No, that doesn't make sense. So that's how you would interpret a continuous variable. That's not how you interpret a dummy coded variable. What this suggests is that whatever you've coded as 1, when you compare it to your reference category of 0, if it's a negative number, it will be lower than. If it's a positive number, it will be higher than. So in this case, we know that females are coded as 1. So we're comparing females to males. So females have 1.66 points lower on the blood pressure measure than males. And so that's how we'd interpret it. So whatever is coded as 1, you think about that and you compare it to your reference category of 0. If it's a minus number, then whatever's coded 1 is scoring lower than your reference category. If it's a positive number, then whatever you've coded as 1 is scoring higher than your reference category. And that's how you'd interpret it. So that's quite often what most commonly that's the approach we use. As I said, if you use things like weighted effect coding or anything like that, then you have to interpret it in a slightly different way. So what mine, actually I did weighted effect coding because I had large numbers of say heterosexual individuals than bisexual and homosexual. So I took into account the fact that I had larger groups, which can distort the differences between different groups in things like regression, ANOVA and so on. And these were all compared in relation to the overall mean. So heterosexuals were less rejecting of myths on average, and bisexuals and homosexual individuals, self-identified individuals, were more rejecting of rape myths. But actually, as we can see, the p-values, none of those comparisons with the average score was statistically significant. But it gives you an idea of how weighted effect coding works in practice. Okay, and there's another example where I used weighted effect coding. But this time, again, not statistically significant. Okay. So, we've talked a little bit there. All of the examples that I had previously were just straightforward single variables. So it was looking at the impact of one predictor on an outcome. But there are occasions where you need to create an interaction term, a product term. And if you're going to do that, then you would always you should always center your product. Center your continuous variables first. Now I did do that anyway. I was already ready when I'd centered all of my continuous variables to create a product term. And what I needed to do was to create a particular interaction term, which was to check for pre-manipulation. So what I started off with in the research was I looked at the way that each of those attitudes and demographic variables predicted everyone's scores on the same measure of gendered rape myths. So ask these myths, the dynamics of rape explicitly ask about victims and perpetrators of different genders. Then what I wanted to do was to look at different stereotypes which aren't necessarily explicitly about gender. If I change the phrasing of the words, so if I ask people to think about, in some cases, to consider the myths in relation to male victims of male perpetrators, to others I asked them to consider female victims in relation to male perpetrators, and so on. So later on in the research, I presented them with a set of new different types of myths, and I asked them to consider them based on victim gender. But I didn't tell them that I was comparing. There are other conditions that they where I looked at different victim and perpetrator gender combinations. So what I wanted to do is to check that there weren't any initial differences between my groups before I manipulated it. Otherwise, it could just be because there were pre-existing differences between the groups. Even though they were kind of randomly allocated to groups, I wanted to check this. So what I did was I created an interaction term based on the groups that they were in. So they were either in the male victim, female victim group, or they were in, and they then read the scenario was either based on a male perpetrator, a female perpetrator, or the perpetrator gender was not specified. So I created an interaction term between the victim gender and perpetrator gender, and I entered that into the model because what I actually didn't want to see, I didn't want to see an effect of that, because that would suggest that there are existing differences between those groups even before I manipulated them. That's what I did. I created an interaction term. And essentially what that means is it's a fancy way of saying you take your two continuous variables, for example, or you take your two categorical variables, in this case, and you create a product term. You multiply the one by the other. Now, it's more straightforward when you're doing things like dummy coding, but I was doing weighted effect coding, so it became horribly, what I felt became horribly confusing. So actually, again, I used that website, and I would really recommend having a look at that. It provides a really good illustration of how you create interaction terms between categorical predictors using different approaches. And so if you're thinking about doing this with your categorical predictors, it's actually more straightforward when you've got two continuous variables. You just multiply them together after you've centered them. But if you've got categorical predictors, you want to look at the interaction between them, have a look at this website. It provides a really good Excel spreadsheet where it illustrates all of them, and you can kind of then use it to create your own terms and take it from there. And that's what it looked like. So I looked at the weighted effect for female victim, male perpetrator condition, female victim, female perpetrator condition, female victim, unspecified perpetrator condition, and so on. And luckily what I saw was absolutely no statistical significant effect. And I did have adequate sample size for this, for the number of predictors that I had included. So my conclusion was that there weren't any pre-existing differences between these groups. If that was the case, then none of these effects, they hadn't been manipulated at this point. None of these effects should have been significant, and they weren't. And so that was evidence that when I did find significant effects later on in the analysis, in the study, then it's possibly due to the manipulation, the condition they were allocated to rather than anything else. So that was that was a really interesting process to go through, but I would strongly recommend, if you're thinking about doing it, look at that website and the resources. They are fantastic. Okay, so what can regression tell you? It can tell you about the cumulative effect of predictors. It can tell you about the relationship between individual predictors controlling for others. It can, if you have no missing data or if you use listwise deletion, it can tell you the unique variance that's accounted for by each of your predictors. So if I go back to this example, this is a percentage of the unique variance because of the way that I handled the missing data. I did a form of iterative imputation of missing data, but so I didn't have to worry about kind of listwise deletion or anything like that. It tells you the unique percentage that effect accounts for. So obviously, because there were no significant effects of these terms, there was no unique variance really accounted for, which makes sense. But you can talk about the unique percentage of variance that's accounted for by an individual predictor. You can look at interaction effects, predicting outcomes, so it's incredibly useful. And actually, linear regression forms the basis of more complicated techniques, including mediation, moderation, and conditional process analysis. Now, there is an additional lecture that introduces you to those things if you should be interested. It is something that a lot of students are now doing in things like their dissertations, and they allow you to explore interactions between variables in more complex ways, and are guided by theory, so the nature of the relationships you expect to see. So if you want to learn more about that, have a look at that video on Blackboard. It's in the same folder as this video. There's also a really useful book by Andrew Hayes. We have a link to it there for the e-version through the library resources. And there's also, he developed a tool called the process tool, which can be embedded into SPSS, that will allow you, in a much more straightforward way than you used to be able to do it, it will allow you to conduct mediation, moderation, and combinations of the two, which is called conditional process analysis. So I won't go any further with that. Right, so what I'd like you to do now is to have a look at the simple linear regression part of the walkthrough that is on Blackboard. Have a go at it, get a feel for running the simple linear regression, the output that's produced, look for things like where your p-values are provided, and so on. And then return to this video. So pause this video, have a go at that, and then return to this video. And we'll talk through how to deal with common help scenarios with your data. Okay, so I'm going to assume that you have finished that. You've had a go at that walkthrough. So some of the common issues with regression, we've already talked about some of these. One of them is that you've got missing data. How do you handle it? Well, there are two core approaches, and we'll talk through that. But that's something really you should be trying to control with research design wherever possible, as is the assumption of independence, which is tested using the Durbin-Watson statistic. Those things are usually checked at the point of kind of research design and starting to get into, and then check, well, you try and control through research design, and then you check them when you come to, you're looking at your data collection and data analysis. The next ones are things that you have to really explore once you've got your data. So things around kind of your predictors and handling predictors that are too highly correlated to each other. If you've got multivariate outliers, univariate outliers, do I need to look at them or not, and so on. You also, what do I do if I've failed the assumption of, violated the assumption of normality or homoscedasticity or so on? And what if my model's significant, but none of my predictors are? What on earth does that mean? Okay, so in each of these cases, don't panic. Okay, so with the first couple, so you've got missing data, and your Durbin-Watson statistic is nowhere near 2. Now, Andy Field suggests that it's problematic if you have a Durbin-Watson statistic when it's either less than 1 or greater than 3. It can only ever go between 0 and 4. So if it's within the bounds of 1 to 3, you're probably okay. Especially with larger samples, you can get away with it. If it's not, if it's nowhere near that, if it's a lot less than 1, well, if it's less than 1, if it's more than 3, you've got an issue and you need to correct for it. And actually, one of the best ways to correct for it is to mean center your continuous variables. So if you've already done that, you're less likely to encounter an issue with that, but it is something you should still be aware of. The issue is that you have to know the order in which the data was collected to be able to test that in a meaningful way. And you have to make sure that your data set is actually ordered in that order, because the order in which you present the cases in the data set will affect the Durbin-Watson test statistic produced. It won't actually affect whether you've violated the assumption of independence or not. It will just mean it'll mask it, it will hide it if you don't put them in the right order. So you should always check that when you're doing that. If you've got missing data, there are 2 core ways of handling it. Well, actually, technically, there are 3. The first one is listwise deletion. If you've only got a couple of cases where you've got missing data on them, then you can use listwise deletion. It's probably the safest method. And this is where it will exclude that case from all regression analysis because it's got missing data somewhere. The alternative, and if you've got more, a fairly substantial amount of missing data, then actually if you use listwise deletion, you can drastically reduce the power of your analysis. So an alternative is to use something called pairwise deletion. And SPSS will ask you this, and if you looked at the walkthrough, you'll see, where in the options it asks you to make that decision. Pairwise deletion is where it retains the case for the comparisons between predictors and outcomes where it has that information, but it drops it for those comparisons where it's missing the data. So it does maximize power. The issue is that you can't interpret things like part correlations anymore. The unique variance accounted for by each predictor, you can't calculate that because those relationships are no longer orthogonal. You can't actually look at the unique variance anymore. So you have to be very careful then in how you interpret your effects. They become more complicated. There is a third option that is provided by SPSS, which is to replace with the mean. In some respects, it's similar to listwise deletion, but I think, and some authors think, it can be misleading because it may boost your sample size, but actually it inflates the similarities between cases, and it reduces the standard error in the estimates, so it can make effects look a lot stronger than they actually are. As such, it's not a good idea necessarily to do that. So I would say limit yourself to choosing between either listwise deletion or pairwise deletion, not replacing with the mean. Okay, so the next kind of thing we might want to think about are the parts of the data assumption checking. So if we're looking back here now, we're thinking about how highly correlated the variables are with each other. So our predictors, we've got predictors that have a correlation of 0.7 with each other. It would be a bit like that moment of in the corner of the emoticon, the scream, no. It's okay to have a strong relationship between a predictor and an outcome, but it's not ideal if we've got 2 predictors that are so highly correlated to each other they're essentially the same thing. And that's because it will throw out the findings of the regression, it will reduce the power, it will mask the relationships between variables and so on. So it's not a thing you want to avoid, which is multicollinearity. But just because 2 variables are highly correlated doesn't mean that necessarily you have multicollinearity. What you have to do to check that is to look at your VIF and tolerance values. And so if the one set of values are larger than 10, you've got a problem. If the other set of values are smaller than 0.1, you've got a problem. Otherwise, you should be okay. And actually, you can get SPSS to produce all sorts of collinearity diagnostics as well, which if you identify you might have a problem, you can use to identify exactly where the problem exists. You have a number of alternatives. You can quite often, if you mean center variables, it can help you deal with multicollinearity. But an alternative is to just separate them out to run separate regressions, or to see if there's a way of combining the two variables into one score. And sometimes, if they're two subscales that come from an overall questionnaire, there might be a way of just using the whole questionnaire score rather than the two subscales at all. So that's one approach again that can be taken to deal with it. But you do, if you have multicollinearity, you've got to do something about it. You also need to explore things like your univariate and multivariate outliers. Now, univariate outliers technically are not part of the assumptions of regression, but they can have a damaging impact. So it's always worth looking over your variables, once you've centered them, to see if you've got any kind of really extreme scores that are standing out, because it may be that those are going to contribute to multivariate outliers, which are a part of the assumptions of regression you've got to deal with. So it's always worth looking, because it may be sometimes that there's been an error in the way that you centered your variables and the way you entered the data in the first place, that sort of thing. So it's always worth checking to see if you have any extreme scores, to see if there are any mistakes. Okay, so I just want to illustrate the impact then of outliers on linear regression. So I'm going to go back to that interactive regression plot that I showed you earlier. Okay, so let's imagine that we're plotting out the line. We're going to just have, I've got all these data points, and okay, they're not all kind of perfectly linear, but there's something going on here. That looks quite good. We can see that overall the correlation between the values, it looks really high, and so on. What happens then if we have an outlier? So an outlier would be one, a multivariate outlier is one where you've got, on a combination of variables, there's something strange going on, something kind of really sits far away from all of the other data points, all the other participants' combinations of scores. So if I put something up here, do you see what happens to the line? Okay, so you instantly see that the correlation between the variables is massively reduced. And you can see that the line of best fit is actually being pulled upwards to try and account for this extreme case. And so now the line of best fit doesn't actually fit anything particularly well. So in trying to account for this data point, it's pulled itself away from the rest of the trend, and now it isn't actually fitting very well at all. And so that's the impact of an outlier. So let's have a look at what that looks like on our residuals. So you can see kind of how we would plot it out. So we can see blah, 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 blah. We go down, look at each of these. Whoa, they've got a really different score to the rest of them. You can see that they're really sitting far away from everything else. And so that's what the impact of an outlier is. And that's why, particularly with multivariate outliers, we need to identify them to look at the case. And we can do that with the SPSS output and decide how to handle that. Because the impact is that it can make predictions on everything else poorer in an attempt to account for this. And what we have to decide is that an erroneous measure? Is there an error in the measurement somehow? And take it from there. But I just wanted to show you that the impact of outliers. So I find this is the best way to do that. You can use things like Mahal's distance to identify if there are any to start with. You could then sort your data in order of the size of the multivariate outliers and see how many there are. But you can also compare it against the Cook's distance value. If you have a Cook's distance greater than 1, then you've got at least one multivariate outlier which is having a substantial influence on your model, and you'll need to do something about it. Again, you could go back into your data set, sort it on the order of size of the Cook's distance, see which cases are causing the problem, double check that it isn't because of data entry errors, but at that point you might either need to think about transforming that case variable, or probably the slightly more straightforward way of doing this would be to exclude it. We run the analysis without that case included, but you have to be clear that that's what you've done when you're writing up. Okay. But there are things you can do. In terms of normal distribution, now it's not the raw data that has to be normally distributed, it's not the outcome score raw data that has to be normally distributed, it's the residuals in the model that have to be normally distributed. Now there are different ways of looking at that. And actually, if you've got a reasonably large sample size, then it's fairly robust to some issues with normality. What you're looking for is roughly normal, not perfectly normal. If you've got a real problem with normality, then there are things you can do. If you're using version 27 of SPSS, you can actually rerun the analysis, but you have to tell it to drop all of the diagnostics and actually to get it to produce bootstrapped confidence intervals and bootstrapped estimates. And those are robust then to violations of normality, and actually they provide a better estimate of statistical significance than a p-value would, which can be an issue. If you haven't got version 27, unfortunately, of SPSS installed, then you're going to have to use some other workarounds. If you look at Andy Field's book, he talks through approaches to doing this, and actually there are some add-ons like the process tool which you can use, and in fact you could actually do the analysis using the process tool that can correct for or robust to issues with normality. But if it's roughly normal, then you should be okay. Again, if you're looking at your standardized residuals and you see that there's a strange curve or a funnel shape, then again you've got a problem. So if it's a funnel shape, so the error is more spread out at one end of the outcome variable than the other, then you've got heteroskedasticity, and that is a problem. One of the approaches is to use the plugin that Andy Field recommends for the robust regression. The alternative is to use the process tool, which can estimate or it can use heteroskedasticity consistent inferences. Goodness, what a mouthful. You can use that then, and it can compensate for that. It is quite a serious issue. If you've got proper really clear funneling, then you've got to do something about it. Alternative approaches are to try and transform your variables in some way, but if you've already mean-centered them, that usually will correct for the issue, or it can correct for the issue. So if you've still got a problem, then yeah, you're going to have to do something else. If you have a curve in the data, what it suggests is that you don't have a linear relationship between the variables. You're going to have to handle it in a slightly different way. So you can't use a linear relationship, linear regression to model those relationships because it isn't straight lined. There are things you can do to try and correct for that, but it may be that you need to look at a different type of analysis. That is probably the more substantial issue that is harder to overcome. One option is, and it depends if this is meaningful or not, but to potentially chop up your outcome variable into two categories and use it something like a logistic regression instead, but that doesn't necessarily get around the issue either. So again, have a look at Andy Field's book where he talks about robust regression and things you can do, but it is the more challenging one to overcome. Finally, the last part is about kind of interpretation issues. So what if I've got this overall statistically significant model, but then I look at my predictors and nothing else is? That's going to be an issue most likely to do with power. You've got enough power to potentially detect the overall effect, but not the individual predictors controlling for the other predictors in the model. One issue is potentially, if you can, to collect more data to boost your sample size. But other than that, it's just being aware that it may be because of sample size issues, a lack of power. So it could be that you could look at something like running a sensitivity power analysis using G-power to see the smallest effect size you could have identified based on the sample that you have. So you could compare that with the effect size that you do have and draw inferences from that. But the only way of getting around that is to potentially collect more data. Or you could consider stripping out a few more of the predictors, being really stringent with which predictors you enter into the model, and looking at a model with fewer numbers of predictors, and that would maximize the amount of data you have. But you have to be careful with how you do that, because it could just be if you're not careful, it just looks like fishing. But that is one approach. So what did I encounter? Well, I encountered quite a lot of issues. So when I was doing my analysis, it was fairly complex. So I actually looked at a range of literature that's just really starting to kind of explore the way that residuals can reveal lots of interesting things about the way that your regression model works. And I've put links to each of these papers in those in the suggested reading. It is really, really helpful. I found, at what point, because I had quite a large sample size, over 500 participants, at what point does skew become a problem? So usually in smaller samples, then if you've got skew over, -1 to +1, then you've got a problem, and same with kurtosis. But when you've got large samples, you would expect to see that more. And so what's the point at which these things become a problem? And so I actually found some really useful information about that with the Cassini and the Kim papers, and I've put links to those later. You're also looking at things like the residuals. Was there anything strange, any non-linear relationships going on? Luckily, with that, I didn't find any problems. But I did find some heteroscedasticity. But I checked that further, and there are some guidelines and things like Tabachnik and Fiddle that talk about how you can assess when heteroscedasticity really becomes a problem. And I found that actually the spread at the widest point was only 1.7 times that of the narrowest point of spread of the residuals, which is if it's within 3 times that, then actually it's usually not too concerning. So I found that actually, based on my sample size and what was going on and the patterns of the data, that I didn't need to correct for overall, because the violations weren't so substantial that they would be causing a problem. But you get a sense of, what the level of detail that you really need to start checking your data if you want to be confident in your findings. Okay, so writing up. The most important thing is, knowing the approach you want to take, and why you're doing that. So if you're taking an exploratory approach, or whether you're going to use standard or stepwise regression, which one and why. If you're controlling for confounders or testing a specific model, if you're going to use hierarchical regression, why you're doing that. Make it really clear based on your hypotheses and how they link to the analysis approach you're going to take. And then obviously that has knock-on effects of things like sample size calculation. So how much data you're going to need to anticipate collecting to be able to look at these relationships in the way that you want to. You should think carefully, if you're doing multiple linear regression, think carefully about whether you need to center the continuous predictors or not prior to entering them. I think a lot of the time centering can help with a whole range of different issues, but sometimes it doesn't make sense to. If you've got a variable in its raw state where a 0 is a meaningful number, then it probably doesn't make sense to center the variable. If you're only doing a simple linear regression with one predictor, it probably doesn't make sense to center the variable, and so on. But have a look at those blog posts I suggested earlier in the lecture for some ideas of when to center and when not to. And as with any type of analysis, evidence the claims that you make about it. So if you say you found a statistically significant result or a non-significant result, provide the statistical evidence to support that. In terms of things like choosing the approach to modelling in regression that you are going to, draw on the relevant theoretical evidence, the empirical evidence, previous research findings to help you do that. And if there are really clear or contentious points in the literature, like the examples on interpreting heteroscedasticity, where I had to really eyeball the data and try and decide how to handle it, make sure that you evidence your decision making using the guidelines you followed, the approach to data assumption checking you've used, and that can give the reader more confidence in the decisions you've made. You can see there's a precedent for doing that. It hasn't just been to make a significant effect significant, whereas if you took another approach, it would be non-significant. In terms of APA guideline, again, it's always about clarity, about being concise, be consistent. there is a recommendation that we report the coefficients, for example. And actually, if you have a look at some of the examples from my chapter, you can include things like model summary data, like your adjusted R squared and overall model fit and model statistical significance and so on, in tables. So really, the APA recommends using tables to kind of to communicate your results. Be clear about the assumption checking you've performed, what you found. Make sure you report descriptive statistics. So often in regression analysis, people focus on the coefficients table without telling us anything about the actual means of the initial variables, or the standard deviations, and so on. So don't forget those. You should talk about kind of things like the model performance statistics, or how good the model is at predicting, because that means we know how much weight to put on any relationships that you've identified between predictors and outcome. You know, how good is this at estimating your outcome variable? As a minimum, you need to report for the coefficients the unstandardized and the standardized coefficients, and the standard error of B, the unstandardized coefficient. And really, you should be now including confidence intervals where you can. Sometimes you have a horrendously large table and you can't fit them in, but if you can, you should. So hopefully by this you've got a sense that the strengths of linear regression is incredibly powerful, it's incredibly flexible. There are lots and lots of guidelines now of how to apply it to different situations to resolve, complex and contentious issues. It can be really useful if you've got quite nuanced hypotheses in helping you to unpick those. It can help us predict, it has a really useful value. And actually, it can be used to explore similar kinds of questions using similar types of data to ANOVA. And sometimes ANOVA isn't an appropriate choice, it's not suitable, and you can turn it into a regression problem instead. So actually it can be really flexible. The problem is that, as with correlation, there's a tendency to confuse prediction with causation, and you have to be wary of that. All we can say is that one thing predicts another. We can't say that this is concrete evidence that one thing is causing the change in another variable. You have to be aware of something called overfitting, and that's where you just put lots and lots and lots and lots of variables into the model, and it can, based on spurious relationships, it makes it look like your model is better than it actually is. So both overfitting and spuriousness can only be controlled really by good use of theory to guide you in your choice of variables to include. You have to be very careful if you're using ordinal variables. So there are arguments about whether Likert scale response options, when it's considered for one item only. So I'm not talking about a questionnaire total score where you add up people's scores on lots of Likert scales to create a total score. But if you've got one item, like how satisfied are you with your life, and you score it from 1 to 5, at that point there's a huge amount of debate about whether that would be an appropriate predictor or outcome for regression, because it is probably ordinal. You should actually be treating it as an ordinal level variable, and it is what we would call, if not range restricted, it's a coarse level variable. Range restriction can also be that people only score within the very middle range of a larger potential range of scores. So although people can score more than that, people aren't in practice for whatever reason. That can cause problems as well. If you are designing then a Likert scale outcome variable about satisfaction with life, the argument is that the larger the number of options that someone can choose between, the more that variable will mimic an interval level. So you want to be aiming for at least 7 points on the scale, preferably more than that if you want to treat it as an outcome variable or a predictor in linear regression. One of the other issues with regression is that you can be very power hungry. You can need large numbers of participants to be able to test, models with numerous predictors. and how you handle missing data, which is, especially if you've got a long study, long questionnaires, for example, you'll have dropouts. How you handle that can have a huge impact on how you, on the bias in the regression model and how you interpret the results. So to understand that more, I'd have a look at Andy Field's book and look at the chapter, The Beast of Bias, so in discovering statistics using SPSS. And as I said, there are ways of producing robust estimates when you violate assumptions, but the issues are that they can be complicated and long-winded to do, and it involves adding in add-ons to SPSS and so on, but they are there. Hopefully then this has given you an idea of what regression is, when you would use it, how it works, some of the issues, things you have to be aware of, and then how you actually communicate your findings as well from regression. So hopefully it's given you a really good foundation in that. Some suggested reading or watching. I would have a look at the Eugene O'Loughlin's YouTube channel. He does have a simple linear regression by hand tutorial. There's also a really good chapter in Julie Pallett's book. She takes you through standard and hierarchical linear regression. There's a range of online resources that Andy Field has produced about bias and using the linear model in regression. And there's also an example where Hayes and Montoya talk you through linear regression interaction with a multi-categorical predictor. So they take you through how you handle that and how you can run the analysis and interpret the findings. So these are the references that we used in this lecture. I hope it's been useful, but thank you very much.